Hello, this is Doug Montgomery. I would like to welcome you to our Fireside chat for this month. This is number 10, by the way. And we record these, as you probably know. And we have posted the previous 9 Fireside chat recordings on Coursera. And it's in the resources tab of your course. And we will post the recording from this session there as well as soon as we get finished. Couple of reminders, if you haven't been here before, this is important. Your mics and your video are turned off. Your mics are muted, and please don't turn them on. And if you want to submit a question to our guest Nathaniel or to me, please do that using the chat function on your Zoom menu bar. And you can do that anytime. You don't have to wait until the Q&A part of this Fireside chat begins to submit the question. You can do it anytime you want during the session. And we will try to answer all these questions in the latter probably 30 minutes of our program today. But if we don't get them answered during this time, we will respond to that in Coursera for the people that are enrolled. And if you'd like to have more details on the question, if the answer doesn't really quite work for you, contact me, contact us, and we'll try to have a little bit more dialogue about this, because I want to make sure that anybody that has a question has a good workable answer for that. So I'm pleased to have as our guest today Nathaniel Stevens. He is an assistant professor of statistics in the Department of Statistics and Actuarial Science at the University of Waterloo. And when I met him, he was a faculty member at the University of San Francisco. And there he was in the Department of Math and Stat, and he was the program director for undergraduate of their undergraduate data science program. And he has been very active in overseeing data science projects and internships. He's been involved with over 30 of these at 20 different companies. So he's very experienced in this area. He's interested in using stats to solve practical problems. He has a passion for inspiring and training students to do the same. His research interests lie at the intersection of data science and industrial statistics. And he's published very widely in topics such as experimental design, A/B testing. And by the way, if you've been attending our Fireside chats, Fireside chat, one of our early Fireside chats had 2 of my former PhD students from ASU that work at American Express, that they're very much involved in this A/B testing. So that might be a Fireside chat you might want to go back and take a look at. He's also interested in social network modeling and monitoring, survival and reliability analysis, measurement systems analysis, and the development of estimation-based alternatives to traditional hypothesis testing. So he's got very wide interests, and he's a great speaker. And we're really fortunate to have him, and he's going to talk today about an extremely important topic that we don't really talk a lot about in our course, and that's the idea of confirmation testing, confirmation experiments. So with that, I'd like to invite Nathaniel to join us, and we'll get his presentation going.
All right, hello. Thank you, Doug, for that introduction, and thank you very much for inviting me. Let me just get this PowerPoint shared. All right, should be up in a moment. And maybe Doug, you can just confirm if you can see everything.
I've got it. It's full screen and I can see everything.
Perfect. Okay, all right. Well, thank you again for the introduction, and thank you very much for inviting me to be here. It really is an honor. And thank all of you who are tuning in either live or maybe after the fact for taking some time out of your day to hear what I have to say. So as Doug mentioned, I'm going to talk to you today about confirmation experiments, both how to think about designing them and then also how to think about analyzing them once you've collected data. And before I get too far, I want to acknowledge my co-author in this work is Christine Anderson Cook. If you've been following along with these fireside chats, you might recognize Christine. She was, I believe, the guest last month before me. She's a research scientist at Los Alamos National Lab, and this is a really interesting bit of work that we worked on in the last couple of years. So just to give you a quick overview of where we're headed in this talk, I want to sort of lay a foundation and explain what the problem is. And for those of you who aren't yet experienced with response surface methodology, I want to provide a bit of context and overview of that as well. I believe that that's in the third course of this Coursera series. So some of you may not have encountered that yet, but I want to make sure that all of you at least have this common foundation. So I'm going to describe the problem. I'm going to talk about probably the most prominent existing solution to the problem, and then talk about some of its, what I perceive as deficiencies, and we'll talk about the proposed solution, both on the design and the analysis side. And then we'll end with a quick example and a summary. So what is the problem? Where confirmation experiments fit is in this broader problem of response surface optimization. So the idea here is that you've got some response variable y that you have primary interest in, and you want to optimize it in some way. And so what that might mean, depending on the context, is that you want to maximize y or minimize y, or maybe hold it on target. And what we do typically is think about how y is likely related to one or more factors, and we want to understand the relationship that exists between them. And so what you see on the right-hand side, this graphic here, this is sort of an imagined response surface, a true response surface between y and these two factors, x1 and x2. And we'll never know this true surface exactly, but we're going to model it with some sort of a model like you see on the left here. And the idea is that through a sequence of designed experiments, we're going to collect data to understand this relationship. And so what that looks like is we're going to consider different experimental designs where we consider different combinations of x1 and x2. So you imagine sort of exploring the floor of this box. We're going to consider different combinations of x1 and x2, and experiment with them, and through that collect response observations at those locations. And through that series of experimental conditions and data collection, we're going to be able to fit models to try to approximate this surface. And the framework that all of this falls within is something referred to as response surface methodology, which is the collection of statistical tools and techniques used for product and process optimization. And we typically think of RSM, as I'll refer to it as the acronym, as consisting of 4 phases. And I want to spend just a little bit of time explaining each of these phases. So the first one is factor screening. And typically when we think about this sequential experimentation, the first thing we want to do is identify which among a potentially large number of factors are the important ones. And in experimental design, we call those active factors. They're the ones that significantly influence the response. And it's typically the case that only a small proportion of all of the ones you might be considering are actually important. So factor screening is meant to try to understand which of those are the important ones. And we typically do this with factorial designs. So we might imagine running just some simple 2-level designs to begin exploring this x1, x2 space. So the rectangle that you see here on the right-hand side, this is the floor of that box that we looked at earlier. And our experiments are going to happen inside this box. And at each one of these dots, we're going to collect data, collect response observations. So in factor screening, we're typically fitting first order models, maybe first order models with interaction to try to understand which factors are important. And suppose that we find that it's just this x1 and x2 are the important factors. Then we might want to start thinking about, okay, which particular levels of these factors, what specific location in this space corresponds to the optimum response. That's our ultimate goal here. And so we need to, in some sense, efficiently search this space to find that optimal coordinate of x1 and x2. And one of the first things you might do is just double check that you aren't already in the vicinity of the optimum. So we can add what we call a center point run here and fit a model that has quadratic curvature in it. But unfortunately, with only the number of runs that you see here, we can't fit a full second order model. So instead we fit one with what we call a pure quadratic term. And we use this to test for curvature. And let's imagine that we don't find any significant quadratic curvature in this region, meaning that we are not in the vicinity of the optimum. So let's carry on. And what we do next is start on this, what we call path of steepest ascent or descent, depending on whether what you care about is maximization or minimization. And so what we're going to use is a first order model to approximate the underlying response surface, and we're going to use the gradient of that first order model to tell us which direction to start heading in as we explore for the optimum. And so imagine we take a couple steps, and at each one of these dots we collect response observations, and we find that when we get here, if we had stepped further, then we would have no longer seen an improvement in the response. So maybe right now we're thinking, okay, maybe we're in the vicinity of the optimum. So let's add a few more runs and do another one of these curvature checks. And suppose that we find we aren't yet in the vicinity of the optimum. And so we need to do a little bit more exploration. So we find that there wasn't significant quadratic curvature here. And so what we do is another path of steepest ascent with another first order model fit using the data collected from the runs in this region. And that tells us to walk in this direction. And suppose now that we've landed here at this coordinate, and if we go one step further, we stop seeing improvement. So again, we wonder whether we're in the vicinity of the optimum. So let's fit another one of these models with the pure quadratic just to double check, and imagine that we find significant quadratic curvature, suggesting that we probably are in the vicinity of the optimum here. And so what we want to do next is move to the third phase of the response surface methodology and actually do response optimization. So what we need to do is fit a full second order model. That's the one that you see on the left here. You can see that the quadratic term has changed relative to what it looked like before. This is a full second order model. And using this, we can identify the location of the optimum. And in order to fit this model, though, we needed extra experimental runs. And you can see these are the additional points. Imagine we do a face-centered central composite design. I'm not going to explain exactly what that is, but just imagine we add these extra experimental runs here, and with the additional degrees of freedom, we're able to fit this full second order model like this. And using this model, we can interpolate and find the stationary point, the location of the optimum. And suppose we find it's right there. Throughout this presentation, we're going to use X star to denote the optimum. And so what we found through this sequence of experiments is that this position X star are the settings of factors X1 and X2 that are going to give us an optimal response. And so you might think, we're done now. We found our optimum. We now know which levels of X1 and X2 are the optimal settings. So what could possibly be next? Well, what we should think about doing next is confirming whether we believe this, whether we believe that this is actually the optimum. And that's the context of the talk today. We're going to talk about how do we confirm that that really is the position of the optimum, and also that to confirm whether the good performance that we observed in terms of response values at that observation are reproducible. Okay, so just to make that goal clear, we're doing two things in these confirmation experiments. We are confirming the optimal factor setting, so we're confirming basically the position of X star, and we also want to try to reproduce the response value predicted by your model at that location. And you might wonder why. Why would we do this? Why wouldn't we just trust what we found in that experiment? Well, one thing to consider is that often there's a lapse in time between when you do that response surface experiment and you identify those optimal factor settings and when you actually put them into practice. And that lapse in time can introduce potentially a drift in how the process behaves. And what you found to be optimal, say, a week ago or a month ago, may no longer be the case now. So if there's time, if there's a separation in time that exists, then you might want to double check your settings. Another consideration is sometimes the experimentation journey that I just sort of described, that happens on a prototype of the production process, or in a lab, or in some sense a contrived setting that isn't exactly the same as just the ordinary process. And if that's the case, you might want to confirm that the good performance that you saw in the sort of prototypical environment actually matches what you see in real life when you implement these optimal factor settings in an ordinary process. Now, both of these may not be a concern if, for example, there was no lapse in time, or if the experimentation happened on the ordinary process. But a final concern that I think will almost always be the case is that the position of the optimum you identified is very unlikely to be one of the design points that you considered. It's very unlikely that, for example, if you imagine the picture we were looking at, that red dot lines up with one of the other dots where you actually collected data. And so it's very often the case that our understanding of the optimum is interpolated. We're using an approximation based on our model. And we all know that all models are wrong, and some are more useful than others. And it's the reality is that there's estimation uncertainty, and we didn't actually observe data at that particular position. We're just using we're basing our decision on a prediction from a model that has uncertainty. And so what's probably a good idea is to maybe collect some data at that location or near that location, and think about confirming these results. Okay, so how do we do this? And Doug mentioned in the introduction that this is something that it often doesn't get talked about, despite it being an important problem. And there are authors who talk about this in the sense of saying, this is an important problem and we should think about it, and confirmation is something we can do, but very little guidance has been provided on the design and analysis side. And I don't want to throw Doug under the bus, because his book is actually one of the only ones that does give some guidance on this. But the lack of guidance in general has led to a myriad of approaches to this in real life. And if you read through research articles by scientists who are actually doing response optimization, and when they do their confirmation experiments, you find that there's an enormous variation in how they're actually designing these confirmation experiments and how they're analyzing them. And what seems common in all of them is that they collect more data somewhere in that design space. But what is very different from one to another is how they analyze that data they collect, and also where are they collecting the data in that design space, and how much data are they collecting. There's a lot of variation there. And largely, I think, because there's not been a lot of guidance from the statistical community. The one notable exception to that is a paper by Willis Jensen, who works at W.L. Gore. And in 2016, he published a paper in the Journal of Quality Technology that really tries to formalize this confirmation experiment idea. And so what Jensen proposed is, once you've identified your optimal factor settings, X star, let's collect more data there. He recommends collecting 5 or maybe 10 observations at that position. And you might look at these numbers and think these are reasonably small numbers. Why wouldn't we consider collecting more? Well, the reality is that this confirmation phase is happening at the end of a potentially long experimental journey where you've already exhausted a lot of resources. And usually there's practical pushback against investing more resources once you already feel like you found the optimum. So for that reason, the reality is that the amount of resources we have at this stage is reasonably small, and therefore the number of experimental runs is going to be typically small. So he recommends 5 or 10 observations at the optimal factor setting. And then what he recommends doing is comparing those observations in one way or another to a prediction interval produced from your model for what we would expect to see a range of sort of expected values for the response at that location. And there's two ways he thinks about doing this. One is to take an average of your 5 or 10 observations and check whether that lies in the interval, or you can construct some more sophisticated intervals that are simultaneous intervals, and then check whether the actual individual confirmation observations lie within those intervals. And so what his proposal effectively does is it asks whether your confirmation results and your previous experimental results are significantly different at the estimated optimum. And so there's sort of two questions that I have in sort of response to this. The first is, what if your understanding of the location of the optimum is incorrect? And we just argued that our understanding of the optimum is based on a model that for which there's uncertainty. So what if your understanding of X star isn't correct? You're putting a lot of faith in that by only collecting observations in the confirmation phase at that position. And second, what if we wanted to incorporate subject matter expertise? As I mentioned up here, the approach that he suggests relies heavily on sort of the notion of statistical significance. But what if we wanted to account for practical significance? And when you read the literature and see how people are actually doing these experiments, they're collecting their observations at the optimum, for example, in a confirmation phase, and then they just compare those observations to what is predicted by the model, and they say, yeah, these are close enough. And if they're close enough, then we're going to consider this confirmation experiment a success. And that's an important thing to take into account, that if there is subject matter expertise that informs what difference is practically meaningful, it would be nice if we could take that into account in our methodology. And so that's exactly what we do. The rest of the talk now is going to be me presenting our proposed methodology. First, I'm going to talk about how we think about designing a confirmation experiment, and then I'm going to talk about how we think about analyzing it. So we begin by imagining we have some overall budget of n confirmation runs. And this might be 5, it might be 10, it might be 3. Context will sort of dictate what this number is, but we're going to imagine that we have some known budget of confirmation runs. And what we recommend doing with those is putting some of those at the optimal settings or the optimal location X star. But let's not put all of our observations there. Let's sprinkle some around that vicinity to sort of gently explore the region around it. And when I say sprinkling, I don't mean haphazardly. We do this very specifically. We do it in accordance with something called an equiradial design. And what that means is that if K is the number of factors that we're considering, then we think about a hypersphere of dimension K, and these runs are uniformly dispersed around the surface of that hypersphere. So if K is equal to 2, the hypersphere is just a circle. And so here's a couple of visualizations of different potential equiradial designs, depending on how many runs you want to put at the center versus how many you want to sprinkle around the edge. And so for visualization purposes here, we've chose capital N equal to 6. And you can see that there are different equiradial designs that we can choose from. And some have more replication at the center. And remember, this center corresponds to the optimum X star. But more replication at the center typically means less exploration around its vicinity. Whereas in the other extreme, we have this sort of pentagonal equiradial design where we've got lots of exploration around the vicinity, but only one observation here at the center. And so there's lots of trade-offs that need to be considered when choosing how we want to allocate our resources to either the center versus the vicinity. And the general guidelines that we provide, subject to the constraint that more is always better, but at an absolute minimum, we recommend there being 6 or more confirmation runs where we put 3 at the center corresponding to the estimated optimum, and then the remaining n-3 are dispersed around the edge of your hypersphere in accordance with the equiradial design. And what this does is it balances exploration, but also gathering information at what we feel is our best guess for the optimum. And having some replication there is good because then we can estimate variability, but we're not solely focusing on that. We're exploring outside as well. Okay, so that's the design. Pretty simple. We say just put some runs at the estimated optimum, but also think about exploring around that. And through all of the data collected in that process, you are going to sort of have a better understanding of the actual response values you can expect in that vicinity of the design space. So how do we analyze data collected in this way? What we recommend doing is using something called comparative probability metrics. And I'll explain what that phrase is in a moment. But at a high level, what we're doing is we're formalizing the comparison of confirmation results to those predicted by your previous experiment. And what I mean by formalize is we want to account for uncertainty, both in the predicted model and then also in the estimation that happens when you're collecting new observations in the confirmation experiment. Because thinking back to what I said is commonly done in practice, someone will take, say, the predicted value, predicted response at the optimum from a model, and then take the average of their confirmation runs at the same point and say, okay, these two, they're close enough. And you know, the idea of close enough, that's an important thing to take into account, but that naive comparison completely ignores the uncertainty associated with the predicted value and the uncertainty associated with the data collection in the confirmation. And so we want to account for that uncertainty. That's something that Willis-Jensen's approach does. But what Willis-Jensen's approach misses is incorporating the practitioner input regarding what difference is considered practically meaningful. And that's something that we are going to incorporate into our analysis. So there's two types of comparative probability metrics that I'm going to talk about, but both of them are sort of predicated on this understanding that we have an idea of what type of difference is practically meaningful and what size of difference is negligible. So we imagine that we have some value delta where absolute differences in response values less than delta are considered negligible. So another way that we can think about this is any response observations lying within plus and minus delta of each other, they would be considered practically equivalent. And this value delta, it's integral to the calculations that we're about to do. So it's important, one, that it is available, but also two, that if you're really looking to make a meaningful comparison, that you think carefully about what that delta value is, and don't just pick something at random. It really should be informed by the context and what differences are or are not meaningful. And so what these comparative probability metrics do is basically, in practical terms, they quantify the likelihood that our confirmation results either agree with or are at least not worse than what is predicted from your response surface experiment. So the first of these probability metrics, it's a bit backwards, is what we refer to as the probability of agreement. And the probability of agreement has been used elsewhere in a variety of contexts to basically replace hypothesis testing in the context of two group comparisons, where you want to compare two things, but you want to account for what difference is practically meaningful. So probability of agreement has been used for the comparison of measurement systems, comparison of survival and reliability curves, and in a variety of different contexts and circumstances. So we're adapting this idea of agreement in calculating the probability to this setting, where specifically this theta A is the probability that differences between the response surface estimates is practically negligible. So just sort of walking through the notation here, YC hat, this is our estimate of the response at the location X, estimated from the confirmation runs. And then at that same point, we have Y hat, which is our model predicted value at that same point. And then we want to ask, what's the probability that this difference is practically negligible? And so that's what this interval negative delta to plus delta represents. It's this range of differences that are deemed to be practically unimportant. And there's lots of sort of math and statistical stuff behind the scenes to calculate something like this. And I'm not going to go into that detail. But basically what I want you to sort of take away from this is that what we're doing is quantifying in practical terms, what is the likelihood that your confirmation results agree with what is predicted by the response surface model. And the value of this is, large values indicate that there's a higher chance of agreement. Lower values closer to 0 indicate that there's a low chance for agreement. And ultimately, we intentionally don't provide guidance on how big does this theta need to be in order to be sufficiently convinced that that you have agreement, and likewise, how small does this have to be sufficiently convinced that there isn't agreement. We leave that choice up to the practitioner. That's something that you get to choose. Whether this value, say it's 0.8, is that large enough for you to believe that you have sufficient practical agreement? Maybe it is, maybe it isn't. That's up for you to decide. The second class of comparative probability metrics is something that we call the commensurate probability. And the reason that we have this is to account for the fact that you wouldn't be upset if in your confirmation analysis you observed better performance than what was observed or predicted in your original experiment. And the probability of agreement I just described is in some sense two-sided. And in that case, or with that being said, the probability of agreement is probably more appropriate when your goal for optimization is to keep a response on target. But if you're doing maximization or minimization, this commensurate probability, which we think of as basically being a probability of practical non-inferiority, it quantifies the likelihood that your confirmation results are at least not worse. They could be better, and we'd be happy with that. And so we're going to effectively, in our probability calculation, just take off one of the endpoints. So just let's go back here for a moment. The probability of agreement, we've got these two endpoints, negative delta, delta. We're sort of doing a probability of containment. In these commensurate probabilities, we just take off those and one of the endpoints and ask what's the probability of, in practical terms, being non-inferior, and which of these you choose, the direction of these inequalities is going to be dictated by whether you care about maximizing the response or minimizing it. And again, the value of these, whether it's 0.8 versus 0.6, you get to decide what size of probability is large enough to provide the conviction that you either have sufficient agreement or non-inferiority. So what are the advantages? Well, first is that we emphasize practical importance over statistical significance. And we're in an era of statistics and statistical practice where this is something that people are emphasizing. We really want to do a good job of incorporating practical information and not just rely on p-values and statistical significance. And with that in mind, we explicitly take practitioner input in both the choice of delta and then also in how big these probabilities need to be in order for you to sort of be convinced. And given the level of choice that the practitioner has, means that this can easily be tailored to any context. And not only are we taking into account practitioner input, though, we still are accounting for uncertainty, both in your original response surface design and also in your confirmation runs. But lastly, I think that fundamentally, this is an intuitive and easily interpreted approach. We're effectively answering the question, what's the probability that my confirmation results are practically equivalent to those of the previous experiment? Or what's the probability that they're practically non-inferior? That's just a very straightforward thing to understand. And there are statistical complications and nuances that are sort of underneath the hood in terms of calculating these probabilities. And whether those are simple or complicated things to do depends a lot on the type of model you're using and the design of the experiment that went into the estimation of that model. But ultimately, the metric themselves, once they're calculated, are very easy to interpret. And so I think that's an attractive thing. So putting it all together, our recommendation for confirmation experiments on the design side is to conduct an equiradial design centered at the estimated optimum with a bit of replication at that center point. And then in terms of analyzing, at any one of the points in this equiradial design, we recommend calculating the probability of agreement or the commensurate probability, whichever is the appropriate one in your case, to analyze that data and to understand how good or bad the agreement is between your confirmation results and what came before. So in the 2 or 3 minutes I have left, let's just quickly go through an example. This example comes from the literature, and I want to make clear they did not follow our design recommendation because that design recommendation was not made at the time of this publication. So I'm going to reanalyze their data and then talk about sort of potential deficiencies that could have been overcome had they used our recommended design. So the context here is not as important for us in this talk as the analysis. What I want you to take away from this is that it was a response surface optimization problem where there were 4 factors being optimized, and they were trying to maximize the response, which is this thing that I have no hope of correctly pronunciating. So we're just going to call it the DPPH, free radical scavenging rate, which is already a mouthful. But so we're trying to maximize DPPH, and they did a 29-run box Benkin design. With that, fit this second order model. What we see here are the significant terms left in the model. And using this model, they were able to interpolate, and they found that these particular settings of x1, x2, x3, and x4 were the optimal ones. At that position, x star, the response was maximized at 0.9142. And the corresponding 95% prediction interval was the one that you see there. And they did the sensible thing, though. They said, let's maybe not trust this number. This is an interpolation. We didn't actually observe any data at this position. So let's do some confirmation. And what they did was 3 confirmation runs at this location. So that resulted in 3 response observations. And with those, they estimated that basically the average response from the confirmation was 0.9006, which is strictly speaking less than 0.9142. Their confirmation experiment in terms of the response observation was slightly inferior to what was predicted by the model, but we wouldn't expect things to be exact. Ultimately, they decided that because this 0.9006 was within 2% of 0.9142, that was considered close enough, and that these results ultimately were a success, suggesting that this identified optimum really were the optimal factor settings. And if you want to think about the Willis-Jensen approach, you would ask yourself whether the average of the confirmation runs or all of them individually, you could think about whether they lie in this interval, and they do. And so that by the Jensen method, this confirmation would also have been considered a success. Now, I want to reanalyze this with our approach. And the fact that they explicitly said that a 2% difference is sort of your threshold of an acceptable difference, we can define that to be our delta. So on the scale of measurement, 2% corresponds to 0.018284, and we can explicitly calculate the probability that the confirmation results and the predicted optimum value are within this plus or minus delta. And you find that when you account for all the different sources of uncertainty, that this probability is only around 0.5. Meaning there's a large amount of uncertainty and a large chance for these things not to be considered practically equivalent. Now, this was a case of response maximization, so we could also do a commensurate probability calculation and ask what's the probability of being practically non-inferior. That probability is a little bit higher, but if you look at the size of the lower confidence bound, it's near 0. So it's suggesting that there's a very large chance, in fact, that your confirmation results are actually inferior to what was predicted by the model. And however, and so what you could take away from this is then, well, maybe the optimum X star still is the optimum, but what we predicted by the model is too good. We're not going to actually realize that good performance. That's one thing to take away. But another possibility is, well, that could be true, but also there could be a better optimum nearby, but they didn't explore anywhere other than X star, so they can't know that, which is where, had they taken the approach that we recommend, they might have found something nearby that was better. So just to end and summarize, confirmation experiments are really important and they should be performed. But little guidance so far has been provided in the literature for how to actually do this. And the recommendation that we make on the design side is to balance information at your current best guess for the optimum, but also to explore gently in the neighborhood around it to see if there are better options nearby. And then in terms of analyzing, we recommend these comparative probability metrics to account for uncertainty in this comparison and ultimately quantify the likelihood that your confirmation results agree with, or at least not worse than what you had predicted previously. So that's everything. Thank you.
Thank you very much, Nathaniel. This is a very informative presentation. And you're dealing with, I think, a really important topic. This is something that I've dealt with in my own practice as a consultant, because I have actually found sometimes reluctance on the part of experimenters to do additional confirmation testing, because in some of the industries that I've spent a lot of time working in, pharmaceuticals, semiconductors and electronics, they've already made a big investment, in the response surface study. And so now you want to, now you mean you want to tie up our equipment for another week doing these additional runs. And, so it's always been a struggle to get people to do this, but it's really important. And, I have sort of a naive suggestion in my textbook about doing this, because it's about all I've ever been able to talk people into doing.
Yeah.
But you have a much.
But your suggestion is a good one, because if you read carefully, and I was looking at it again yesterday, yeah, you recommend not to do your confirmation at a design point that you had previously considered. And that's a really important recommendation. Yeah. And I think that ultimately Willis was trying to sort of formalize that recommendation that you gave by incorporating prediction intervals and things like that.
Right.
But even still, it seems like in practice, and you may have experienced it in real life, but even just reading papers, you see that people just compare two numbers that they have and they say, are these close enough? And and that's intuitive, but ignores uncertainty, and so it could be misleading.
Yeah, I thought getting them to at least look at the prediction interval was was a step forward. By the way, it occurs to me, and having looked at what you've done, what you're suggesting is this really kind of close to equivalence testing?
Yeah, that's a really good question. So the probability of agreement, which was sort of the first of these comparative probabilities that came out, I originally thought of that in the context of measurement system comparison. That was what I worked on in my PhD. And as I was sort of thinking of this and trying to incorporate practical equivalence, I stumbled across this idea of equivalence testing, which just sort of, for any of you who are not aware of what this is it just totally turns traditional hypothesis testing on its head, where ordinarily you think about if you're comparing two groups, your null hypothesis is that they're equivalent. But that's often not an appropriate baseline assumption, because the way we know hypothesis tests work is that with more data, you get evidence against that null. And it's often in practice more useful to think about phrasing the null as these two things are different, and we want to search for evidence to the contrary, which is to show that they're similar. We don't want to assume they're similar. We want to show that they're similar. And so there's this whole sort of literature on how to do hypothesis testing in that framework. So what we recommend here, this whole idea of probability of agreement, is similar in the sense that we have this notion of a sort of an equivalence region, the idea of a practically meaningful difference. What's different though is that we focus on estimation, whereas if equivalence testing is still at the end of the day a hypothesis test with a test statistic and a p-value, and given people's misunderstandings and misuse of p-values, we have intentionally sort of framed these solutions as estimation problems that avoid p-values altogether. But there certainly is a connection between what we recommend in equivalence testing.
Yeah, I think that's a good direction to go in. I've run into equivalence testing and working with people, and for example, in the pharmaceutical industry, where you're trying to demonstrate that the efficacy of this particular formulation is not significantly practically different from the efficacy of an older version of the drug, or a competitor's version of the drug. And this happens sometimes in developing genetic drugs. So
it's very, very common in pharmaceuticals.
Yeah,
when you're comparing like a brand name drug to a generic one, you don't need them to be identical, but there's a sort of a threshold, a tolerance of equivalence, where as long as they're close enough, then
it's okay.
Then it's okay.
Yeah, and this is in that same vein, and I think it's really a great move forward in this area. So we have some questions. We have 5 questions. Oh wow. Okay, so let's see if we can get most of these done in the roughly 15 or so minutes that we have left. This is interesting. I'm a data scientist at a company in California. I'm testing a hypothesis using highly right-skewed data that are decidedly not normally distributed. And the central limit theorem applies to sample means, and the size of each sample is over 3,000. Wow, with 80% power. Is this a reasonable assumption given the data are not normal? Yeah, with a sample size of 3,000, I think you can probably be comfortable in invoking the central limit theorem, even though the data is pretty clearly not normal. And he says the power is 80%. With a sample size of 3,000 and the power is only 80%, you must be looking for an infinitesimal difference. And so can outlier removal be done before calculating the power? I'm always reluctant to remove outliers from sample. I've seen so many cases where that's not not a good thing to do. So I would not be too keen on doing the outlier removal. Nathaniel, do you have some comments about this that you'd like to add?
Sure. Yeah. I also, when I think about power calculations, I think about doing those before we collect data.
Yeah.
To determine how much data to collect. So at the moment of a typical power calculation, you wouldn't know if you have outliers yet. If you're trying to do sort of an post-analysis power calculation,
which is what this seems like,
which I think is what this suggests. Mm-hmm. I would agree with Doug. You wouldn't want to arbitrarily remove outliers. If you identified that they were truly a misrecording or an error in measurement, maybe. But if you've got no real sense for why it's an outlier, I wouldn't just arbitrarily remove it.
Yeah, I'm always afraid to get rid of observations that just look unusual. You really want to know why.
Yeah.
Okay, so this is a forecasting related question. He's desired to make a prediction over a time series, which is nonlinear, third and fourth order trend. What methods would be preferable, and what should be considered in this selection? Well, if by nonlinear and third and fourth order trend, I think we're talking about highly non-stationary data.
Yeah.
Would you agree, Nathaniel? I think that's highly non-stationary data. So I always tend to think about some sort of maybe ARIMA modeling as a strategy. You might also think about something else. If there are cyclical components, you might think about some sort of regression type model too, that that would account for the non-stochastic part of the time series.
Right.
But I would probably be headed in the direction of using ARIMA models to do this. And the rule of thumb that I've always used in doing ARIMA modeling is that you probably need at least 60 to 75 observations to get a reasonable ARIMA model, because you're going to need to look at sample autocorrelation and partial autocorrelation functions, and you're going to want to look at least 12 to 15 lags on that function, and
maybe more if there's strong seasonality.
Yes, maybe even more. And if you look at the standard errors of those functions, the estimates become unreliable when the length of that autocorrelation function is about 1/4 of the number of runs. You know, so if you have 75 runs, then you're going to be able to get pretty reliable estimates of your sample autocorrelation function to about 15 lags, let's say. And again, you may need more than that if there is a lot of strong seasonality in the data. So
yeah, in that case, you want to observe a handful of periods to make sure that you're really understanding that seasonal component.
Absolutely.
That whole Box-Jenkins framework for modeling, I think, is very appropriate.
Yes,
here.
I think
you could also consider exponential smoothing, maybe.
Yeah, smoothing methods could be useful. You know, you might do some differencing to get rid of the trend part of the data, and because if it's a very nonlinear trend, I'm guessing that means that the slope is changing through time, and so there's several different modeling strategies, but I really would start, I think, looking at ARIMA modeling as the start, and then maybe I would think about maybe some sort of I think in my time series book we call these direct smoothing models, using Robert Brown's terminology from the 60s, and those are all methods I'd think about.
Yeah.
Okay. 3 general questions to the DOE course. I took a similar course during my postgraduate study. Okay. The lecturer mentioned that DOE is to figure out the causality instead of correlation. Okay. 3 questions. 1, may I know what your comment is about this statement and how can I understand it? Well, I think if you, I go back to my first job at Union Carbide. Okay. And my boss at Union Carbide told me, he said, Doug, if you want to find out what happens in this reactor when you change a factor, you actually have to change the factor. And right away, I understood that gee, observation can tell you something about a correlative structure, but to really understand whether there's a cause and effect, you actually have to change the factor. And designed experiments do that. If the statement is true, is there any mathematical theory to support it? Well, that's the whole context of experimental design. And by the way, if you really want to see a beautiful illustration of nonsense correlation, take a look at the example on mental defectives and BBC radio receiver licenses. It's in my experimental design book, because it's already right in my regression book, because it shows you that there's an almost perfect correlation between the number of mental defectives identified in the UK every year between about 1915 and about 1930, and the number of radio receiver licenses issued. So if you believe that correlation and causality are the same thing, that says that buying a radio receiver license causes a mental deficiency in the British population. And I don't really think that's true. And how can we do causality inference or inference learning from DOE? Well, that's the whole basis. That's what you're doing when you identify significant factors, or when you build a response surface model, for example. That's to me the identification of causality. You have some other comments on this, Nathaniel?
Sure. Yeah, if this person is looking for sort of other mathematical theory, another discipline you can look at is the discipline of causal inference.
Oh, yeah.
Which, you know, those people are trying to make causal conclusions when you can't run an experiment,
Right.
and they're trying to use observational data and have a look at how hard it is for them to do that.
Yeah.
And all of the sorts of assumptions they need to make in order to try to do causal inference. So
Yeah.
if that's really what your goal is, then you know the traditional designed experiment is the best way to do that. But sometimes it's not possible or unethical or whatever the case may be. Causal inference is an alternative that you can look into.
Yeah, but the golden approach is some sort of designed experiment.
That's right.
Okay, let's see what else. Oh, end of questions. Oh, wow. Okay, we knocked those out pretty quickly. We do have another chat coming up on April 14th, usual time, 9:30. Our guest is Dr. Alex Hanlon from Virginia Tech, and she's going to talk about a really interesting topic. She's going to talk about clinical trials. And this is something that everybody is probably interested in, and it's something that we don't talk about in our course at all, because I am not an expert on clinical trials. And I have one PhD student that's what she does. It's not Alex, but this is a really important topic, and I'm looking forward to having her. And Nathaniel, I can't tell you how much I appreciate you coming today. And oh, there's another question that has just rolled in that I think you're going to have to talk about. It's directed specifically to you. It says, could Nathaniel tell us about his experiences with A/B testing?
Yeah, that's a really good question. That's something that I've been thinking a lot about over the last couple of years. So if this is a phrase that you're unfamiliar with, it's sort of, you can think of it as synonymously with designed experiments, but largely in a data science context, where the context of experimentation is on the internet, you know, on websites or apps on your phone, you know, Netflix on your TV, those sorts of areas. And so it's a really interesting application area of designed experiments. There are, I would say, there's currently, I think, a mismatch between what most data scientists are aware of in terms of designed experiments and that whole discipline that you're learning in this sequence of courses, and what they actually do in practice. So often these turn out to be very simple two-group comparisons, a t-test or maybe a chi-squared test. And that's where the phrase A/B testing comes from, you know, version A of my website versus version B of my website. Now, I don't want to sort of discredit everything that's going on, because there are some companies who are doing very sophisticated online experiments. For example, Lyft, the ride-sharing app, they were one of the first companies in this space where I noticed them doing response surface designs. So when I saw that, I realized that, okay, not everybody doing online experimentation are doing overly simplistic things. Some people are sophisticated. So it's a really interesting and booming area of design and analysis of experiments practice, and definitely exciting. There are at the same time many different problems that they experience there that we don't think about in our traditional design. For example, if you're somebody who deletes cookies or uses incognito web browsers or something like that, you might end up in two different experimental treatments in the same experiment. You could both be in the control group and the treatment group. And there's this whole issue of, you know, identifiability of the experimental unit that we traditionally don't run into in and sort of manufacturing or even clinical trial type experiments. So there's a lot of different nuances associated with online experimentation and A/B testing that I think it's worth some statisticians looking at, but definitely an interesting area to look into.
And as I mentioned earlier, we have a previous fireside chat with two of my former students that are at American Express. Edgar Hassler is one of them, and those two guys did a great job of talking about this. And you could go back and find that previous fireside chat. Megan, I think that's chat number 2, I believe. Yeah, fireside chat number 2. And those guys did just a great job of introducing this whole topic and talking about what they do at American Express. And they seem to have a pretty good practice as to what's going on there.
Yeah.
Okay.
If you want more information, this is here we go. This is a good book. It was recently released, I think 2020. These are writers from Airbnb, LinkedIn, and Google. So very, very good book, just to introduce you in a very non-technical way to this world of online.
What's the title again?
It's called Trustworthy Online Experiments, a Practical Guide to A/B Testing.
Oh, great.
So Ron Kohavi used to be director of experimentation at Microsoft. He has since moved to Airbnb. Diane Tang is at Google, and Yaju is the director of data science at LinkedIn.
Great. That's a very valuable reference. I'm not aware of that book. I'll have to get that myself and read it. My two former students, Anson Park and Edgar Hassler, they're probably very familiar with that. I'll harass them about that. Okay. Okay, Nathaniel, thank you again. I appreciate your taking time. You've got a lot going on. You're a busy guy, and I appreciate your spending time with us.
No, thank you for inviting me. It's an honor.
Great. Okay, folks, we're done, and we'll be back again in April.